Hi, and welcome to this finance lecture for Stockholm Business School. I will talk about time value of money, and more specifically, the present value of a perpetuity. First, however, some repetition. We said that financial decisions was about giving up resources today in the hope of obtaining something good in the future. And to be able to compare the resources we give up today with the good stuff we get in the future, we need the time value of money, which basically is that we prefer money today to money in the future, which is due to inflation, interest rate and uncertainty. We also provided some formulas for moving money. So we said that the future value of some cash flow today, we can call that cash flow C, is given by multiplying it with 1 plus the interest rate, R here is interest rate, raised to the power of n, where n is the amount of years we want to move it. We said that we can also do the reverse, so we can take some future value, C, we can divide it with 1 plus the interest rate, where R is interest rate, raised to the power of n, which is the amount of years we want to move it, to get the present value. So if we get the cash flow C in n years, we can divide it by 1 plus R raised to the power of n to get the present value of this cash flow. We also talked about net present value, which was the present value of the positive cash flows minus the present value of the negative cash flows. So basically you take the present value of all cash flows, and this is called the net present value. We also talked about the present value of an annuity. We said that if we have a stream of cash flows of equal size, and if it is exactly one period between every cash flow, we can calculate the present value of this annuity or this stream of cash flows using only one formula. And you can see the formula here. So you take the cash flow, divide it with the interest rate. You multiply this with the factor 1 minus 1 divided by 1 plus the interest rate raised to the power of n, where n is the amount of cash flows in this time. We also said that we can calculate the present value of a growing annuity. If it is an equal growth between any two consecutive cash flows. So if the growth between the first and the second cash flow is the same as the growth between the third and the fourth cash flow, we can calculate the present value of this cash flow stream using only one formula, as you can see here. You should also remember to use brackets here, here, and here. In the last lecture we talked about equivalent annual annuity, and we said that the equivalent annual annuity of some present value is calculated as follows. Basically you divide the present value with the formula for present value of an annuity. So you do the absolute reverse as you did when you calculated the present value of an annuity. And hence you get the reversed answer. So instead of getting the present value, you get the annuity. So obtaining some value today, the present value, is equally good as obtaining another value, the equivalent annual annuity, every year for n years, if we discount all future cash flows with this interest rate. And now we will expand the model And we will talk a bit more about present value of perpetuities. So what is a perpetuity? A perpetuity is an endless stream of cash flow. So what we do is that we calculate the present value of an endless stream of cash flows. So it might look like this, and imagine it continues into infinity. And if we have an infinite number of cash flows, we call it a perpetuity. So we can have an introductory example, so to speak, which is a bit interesting. On November 27th in 1895, Alfred Nobel signed his third and last will, which said that he left the main part of his wealth for the establishment of a prize. The capital was governed by a foundation that would invest the capital in safe investments. The interest from these investments should be distributed annually to receivers of the Nobel Prize. So basically, he willed a lot of his leftovers to the future Nobel Prize winners. And we can assume the following. Each year the Nobel Foundation wishes to distribute a total prize sum of 40 million Swedish kroners, 5 awards and 8 million per award. And the foundation gets an annual return of 2.33% on its investments. So the question is, how much money does the fund need to have available to keep the same price level forever? Well, this is a quite interesting question, because if we know how much money you need to have on the account to be able to give the Nobel Prize winners a sum of 40 million each year in infinity, which was the thought from the beginning. So we can see this as a timeline with an infinite number of cash flows. Yeah, something like this, where we will want to each and every year hand out 40 million, and this will continue forever. We assume that. In order to know how much money we need on the account today, we discount all of these cash flows, this infinitely many cash flows till today. So if we do that and use the regular present value of an annuity formula, as you have seen before, we can do that by taking 40, which is the annual price sum, divide by the interest rate, 0.0233, times the factor 1 minus 1 plus 1, 0.0233 raised to, well, now we have a small problem. We cannot raise to infinity, and if I want to do that, I need to introduce limits, which I will not do, but we can just say I raise this to a something very, very large. You can imagine if we raise 1.0233 to, let's say, 1 million, it will become a very, very large number, because this is over 1. Just since this is larger than 1, if we multiply something larger than 1 with itself like 1,000 times, we will have a very large number. And you can imagine when this a here goes towards infinity, So we multiply something larger than 1 with itself infinite many times. Well, it will become infinitely large as well. This is quite abstract and you don't need to focus that much on it, but if we divide 1 with something that becomes infinitely large after a while, it will tend to go to 0. You can try to divide 1 with I don't know, 50 million, and you will see it becomes a very, very small number. After a while it will be 0. So then it basically says that you should take 40 divided by 0.0233 times 1 minus 0. That didn't look so good. So this is very sloppy notation, but I just want you to get a feeling. And well, 1 minus 0 is 1, right? So we can write this as 40 divided by 0.0233. And we would get 1716.74. Yeah, you don't see it that well, but a bit over $1.7 billion, or Swedish kronor, sorry. So in order to give out 40 million each year for infinity, the fund needs to have a bit over 1.7 billion Swedish kronor on the account today. Because if we have that and get 2.33% interest rate on our investment, we will be able to hand out 40 million Swedish kronor every year for infinity. So this was just an introductory example so that you see how it's actually used in reality. I understand that it's a bit abstract and complex perhaps, but as you saw, the formula becomes very simple actually when we calculate the present value of a perpetuity. However, if we would go to the definition, a definition of the perpetuity is a stream of equal cash flows at regular intervals, and the stream continues forever. It's an infinite number of cash flows, as we showed before. And there is a perpetuity formula where the present value of an infinite cash flow stream, where each cash flow amounts to C and the interest rate is R, is, as it says here, the present value is equal to this C here times 1 divided by R. Or if you want to, you can say C divided by R. It's the same thing. So if we compare it to the present value of an annuity formula, the one we had before, you can see here that it's basically only this part that we can take away, which is because of the reason that I told you before. When n becomes infinitely large, this value here will go to infinity, while this will go to 0, hence this will go to 1. And we only have this part left. So it's perhaps the simplest formula, even though it's perhaps the most abstract part of the present value lectures. So if we take an example, it could be like, examples of perpetuities. We have console or perpetual bonds in the UK. We have cash endowments to business schools and real estate. However, I don't know if we can say that real estates are forever or for infinity. It's if you start to think about it, it's very abstract, and I mean, you can go how long you want in discussing infinity. We will not do it now, of course, but at least you can think about it at home. It would be good. And also preferred stock, where the company is promising to pay a fixed dividend for forever. Of course, however, we don't know if the company will exist forever. So it's defined as a perpetuity, but we don't really know. So here's an example. You won first prize in a lottery and you will receive a payment in 3 years You will receive a payment in 3 years' time of 5,000 Swedish kronor. To make things even better, you will receive a payment every year from that point. So you will receive 5,000 in 3 years, and then you receive 5,000 every year after that. And the question is, what is the present value of your prize if you discount this with 12%? So this is what it looks like. In 3 years you get 5,000, and then you get 5,000 every year for infinity. And the present value, we want to take all these cash flows, we want to move it till today, as we have done before. However, as you might remember, we said that the present value of an annuity formula takes the annuity or all cash flows and transform it to a value 1 period before the first payment. So in this case, we get one single value in year 2. This is, however, not the present value. The present value is in year 0. So we need afterwards to move it again till today. So we take one thing at a time. Start off with, we calculate the year 2 value of this annuity or this perpetuity. And then we take 5,000 and use the formula and multiply with 1 divided by R, which is 12%. Which is 41,666.6667 approximately. So now we are in year 2, and we want to have it in year 0 or today. So in order to get it till today, we conclude that this is a single value, it's one cash flow. And we move single cash flows using the single cash flow formula. And we can take 41,666.667 something and divide by 1 plus the interest rate, which is 12%, raised to the power of 2, because we want to move it from year 2 to year 0, which is 2 years. And if we type this in, we get 33,216.66 0.41156. So the present value of getting 5,000 every year for infinity, will start in 3 years, is 33,216 if we assume that we have a discount rate of 12%. So let's take a final example. And this is the same example as before, but we allow for a growth of 5% between every year. So it would look like this. The first year, or year 3, we get 5,000. And year 4 we get 5,250, and so on until infinity. And between every year we get 5% more than last year. So if we should calculate the net present value of this cash flow stream, it might be a good idea to use the present value of a growing annuity formula, as we have used before. So we can take here the first cash flow, which is in year 3, take 5,000, divide by the interest rate minus the growth, so 0.12 minus 0.05 times the factor 1 minus 1 plus the growth, divided by 1 plus the interest rate, erased to, well, infinity. I cannot raise something to infinity, but we can raise it to a and let a go towards infinity. Well, I will not go into detail about how you would actually do it mathematically, but we can reason, and we can say that 1 plus 0.05 1.05 will be smaller than 1 plus 0.12. So smaller than 1.12. So if we will multiply 1.05 with itself infinite many times, it will still be smaller than 1.12 raised to an infinite number, or multiplied with itself infinite many times. Or more correct, this term will go towards infinity faster than this term. You can, just to get a feeling, you can raise it to power of 100, for example. And if we do that, if we take 1.05 times itself 100 times, we will get 131 approximately. And if we multiply 1.12 with itself 100 times, we will get 83,522. So already after 100 years, this term is a lot bigger than this term. So what will happen is that this whole term here will go towards 0, just as in the previous case. Not as fast, but it will go towards 0 when a here goes towards infinity. And since this will be 0, this will be 1, and we are left with 5,000 divided by 0.12 minus 0.05. So as I said, you don't need to focus about the mathematical part. This is in no way a good mathematical representation, but my point is that it should give you a feeling of why the formula looks like it does. And the most important part is that you understand the formula that you use, which is this one here. This is the formula for present value of a perpetuity with growth. And we have it here. So if you include a constant growth between every two cash flows, you get this formula, where the present value of this cash flow stream is the first cash flow, perhaps we should do like that, divided by the interest rate minus the growth. And it is important that the interest rate is greater than the growth. Well, why is that? We can just go back to this slide, and if we imagine it would be the reverse, we have a 5% interest rate and a 12% growth. Well, then this term will go towards infinity faster than this term, which will make this here infinitely large. So this would be go towards minus infinity, and this here, you will have a true mess. Basically, you will not get an answer because the present value will go towards infinity. That is definitely not something you need to focus on, but remember this formula and try to understand at least somewhat why it looks like it does. So if we should compare to the present value of a growing annuity formula, this is the case. You just get rid of this part due to the reason I tried to explain earlier here. And you're left with this part here. So to summarize, an infinite cash flow stream is called a perpetuity, and we calculate the present value of such a perpetuity in the following way. We multiply the cash flow with 1 divided by the interest rate or the discount rate. And an infinite cash flow stream with a constant growth between any two consecutive cash flows is called a growing perpetuity. And you have the following formula to calculate the present value of such a growing perpetuity. You take the first cash flow, you multiply it with 1 divided by the interest rate minus the growth. And you should remember that the present value we get is expressed in the year preceding the first cash flow in the stream. So it does not need to be in present terms, so to speak. As we saw in the example, we got the value in year 2. That can, of course, be the case in other examples. And it's important to remember that always when you use some present value of an annuity formula, you have 4 now, you will get the value in 1 year before the first cash flow. So if the first cash flow comes in year 1, you get it today. If the first cash flow comes in year 10, you get it in year 9. And it's important to remember that. And each cash flow needs to be equally big, or the growth between two cash flows need to be equally large. And that was all for today. Thank you very much.